Welcome to 15.7 exponential decay function. And just like the previous one, you will want a calculator. And so pause and go get a calculator if you need to. Your phone, if you have one, smartphone, has a great one. And if you didn't know this, on your iPhone, when you tilt the calculator to the side, you get a more advanced calculator. So we're going to be doing decay functions, which means decrease. So we'll be decreasing by 1%. So what's 30% less than 100%? Right, 30% more, you would add the 30%. 30% less, you would subtract it. So if you go down 30%, you end up at 70%. We're going to need that for the next problem. The number of students in a school is projected to decrease 30% per year. If there are currently 400 students, how many would there be at the end of a year? Well, one way to do it, right, you do 400 times 30%. Now, 30% is 0.3 as a decimal. The shortcut is move the decimal twice, get rid of all that. And so you decrease it by 120. That's not the answer, right? You have to subtract the 120 from the 400, and you get 280 students. The faster way, which I indicated yesterday, is if you're at 30% less, that means next year there'll be 70% of the current number. So we literally can just multiply by 0.7 and get it done in one step, as long as you can do 100% minus 30% in your head, which I think you all can. Now answer the next question. Remember yesterday there was something tricky about this. Yeah, if it's 30% again, you have to subtract 30% from the 280. And so it's 70% of 280. 7 times 0 is 0. 7 times 8 is 56. And so there will be 196 students after 2 years if you're decreasing by 30%. So notice you cannot just subtract another 120 because that 120 is 30% of 400, right? You would get the wrong answer. In that second year, you have to decrease by 30% of the 280. So if there you have a nuclear accident or nuclear waste, that decays or diminishes following an exponential function. And we'll do a problem like that later in class. Most tournaments, soccer tournaments, tennis tournaments, doesn't matter, follow an exponential decay function. So there's a very famous college basketball tournament with 64 teams. So that's our y-intercept. And, right, the y-intercept goes there. We're going to have a fraction, right, as our base because we're going down. And we're eliminating half the teams, right? If you eliminate half the teams, so we're just decreasing at 50%, right? You have 50% left. So that's where this 1/2 comes from, the half that are left. And there's the function. And t there is time for rounds. So we're going to evaluate that for f of 4 equals 64 times 1/2 to the 4th. So 1/2 to the 4th is 1/2 times 1/2 times 1/2 times 1/2, which is what, 816. So we have 64 times 1/16 canceling, and we'd have 4 teams. Yeah, and in this famous basketball tournament, they called this the Final Four when you get to that round. Now, if you look at your notes, I wrote this backwards on the notes. The one on the screen is correct. The notes are wrong. You couldn't actually do the problem that I wrote there. That's why I had to fix it. All right, so a game show eliminates 1/3 of its contestants, meaning 2/3 are left. So let's write an exponential function for this. All right, so it starts with 81 contestants. And we need a fraction in there now, right? We eliminate 1/3, right? And so if you eliminate 1/3, you end up with 2/3. So 2/3 is what's in there. And it's 2/3 to the t. Now we're going to see who's left after 4 weeks. So 81 times 2/3 to the 4th. So what's 2/3 to the 4th? 2/3 times 2/3 times 2/3 times 2/3. 3 times 3 times 3 times 3 is 81. And 2 times 2 times 2 is 8 times 2 is 16. So we have 81 times 16 81st, and these cancel, and you get 16 contestants, and it's a word problem. And we should be putting words on every answer. Now, that's the quick way to do it with exponential functions. Now, you could do this with 7th grade skills, and I just want to show it. So if you have 81 contestants and you get rid of a third of them, right? So 1/3 of 81. Well, 3 goes into 81 27 times. So you'd get rid of 27. So after 1 week on the show, right, you would have 54. And then you get rid of 1/3 of those. And 1/3 of 54, I think, is 18. And so you'd have to subtract 18 from that, and you'd get 36. Then you'd get rid of 1/3 of that. 1/3 of 36 is 12, and you'd get rid of those 12, and you'd be at 24. That's 3 rounds. We did 4 rounds. And so then 1/3 of 24 is 8, and to get rid of those 8, and we'd be down to 16. So you could do it that way, way slower, and I did that really fast because I've done the problem before. All right, so we're going to be decreasing most of the time by 1%, right? Yesterday, or in last lesson, we were increasing by 1%. So this is back to the one we did in the warm-up. The number of students at a school is projected to decrease 30% per year. If there are currently 400 students at the school, how many would there be at the end of 3 years? So we did, right? We started with 400. There's our y-intercept. We figured out 70% of that, right? We multiplied by 0.7, we got 280. We multiplied by 0.7 again, we got 196. So, right, we could take 196 and multiply by 0.7 and get the next answer. But let's do it using exponential functions. So it's f of t. The y-intercept is there. It's the first number. Right now, if you this 1 minus r, what that's about, that's the 100% minus the 30%. They're just writing it as 1 minus 0.3. Well, what's 1 minus 0.3, or what's 100% minus 30%? Well, that's 70%, and we write 70% as a decimal. So we'll have 70% left, and then we're going to do t, and our t is going to be 3. So this is where we might want to get out our calculator. And notice, if you've done all the work that we did in the warm-up, maybe it'd be faster just multiply by 0.7. But let's assume that we haven't done all that. And we have to do 0.7 as our base, right? You find this key on x to the y. So you do 0.7 and hit that. And you plug in 3 for the time. And you get 400 times 0.343. You multiply those two, and you're going to get 137.2. So these are students once again, so we're going to round it. So I should be using an approximate symbol. So we'll round 137. All right, so do the same thing for 4 years. Again, we could take 137 and multiply by 0.7 and get 70% of that, or we can use exponential functions. It's 400 times 0.7 to the 4th power. So 0.7 to the 4th power, I'm getting 0.2401. I have to multiply that times 400. And you get approximately, it's 96.04, but approximately 96 students are left. So we're decreasing by 30% per year, fewer and fewer students. Right, so when you buy a car, a new car, I'm talking not a classic car, when you buy a new car, the value of the car decreases greatly the minute you drive it off the lot. You drive it off the lot and you try to go and sell it right away, you don't get the $50,000 that you wanted to pay for it, which is very frustrating to parents. And it's why a lot of parents buy used cars. You save a lot of money when you do that, although people like things that are new. All right, so a $50,000 car loses about 20% of its initial value per year. Find the value of the car after 2 years. So it follows an exponential function. And so it starts at 50,000. Yeah, you're going to want a calculator. Now, right, it's 20% less per year. So where are we going to be? We're going to be at 80%. So this is 0.8. In 1 year, it would be 1. In 2 years, it'd be t equals 2. So we get out our handy dandy calculator, and 0.8 to the second power, right? You could actually do that in your head, right? 8 times 8 is 64. It's 0.64. And we have to multiply that times 50,000 and times $50,000. And so a year later, this is exact actually, right, it would be worth $32,000. Yeah, so it's cost you what? What's 50 minus 32? 18. It's cost you $18,000 to drive that car for 2 years, plus all the maintenance you had to do, assuming maintenance wasn't included in your purchase. Let's find the value of the car after 7 years. Right, so we're assuming that it's going to continue to lose 20% per year, so it's going to be 80% of the previous value every year. And so now we're going to do 0.8 to the 7th. This is bad news for your car. All right, so we get 50,000 times 0.2097152. It's around 0.2 or 0.21. We're going to multiply that times 50,000. And now the car 7 years later is worth $10,485.76. All right. So it was worth 50,000 when you bought it, but now it's worth only a little more than 10,000 7 years later. That's roughly accurate. Now, we sort of did that backwards the way we originally did them. All of those, right, we had a y-intercept that wasn't 1. We're now going to do the ones where you have a y-intercept that is 1. There it is right there. So, right, you read a lot of reports about animals going extinct because of environmental factors or hunting or whatever. And typically, extinction levels follow an exponential decay. Now, if you do something to intervene, like save the animals, then it stops following that. But generally, it follows not a linear function, but an exponential decay function. And let's see that. A rare species of animal is losing 5% of its population per year. What percent will be remaining after 6 years? All right, so it's f of t. Right? We don't have a y-intercept, it's 1. Now, if we're losing 5%, right, we're at 95%. So it's 0.95 to the t. So we're going to have to do 0.95 to the 6th. So let's do that. 0.95, y to the x, 6, and at this point, it's approximate because I'm not going to round it. I get 0.7350. I get a bunch of other numbers. So let's make that back to a percent, right? That's around 73.5 or around, so well, we should round up to 74%. All right. So if you're losing 5% of the population, you can't just subtract 5 times 6, 30, right? That would be what linear thinking. And notice what happens when you do that. You get 65%. It's worse. And this is actually what happens, is that a lot of people do not understand exponential functions. And so they think linearly. Oh, if it's losing 5% every year, 6 years from now, it'll be at 65%. And then 20 years from now, it'll be at 0. It doesn't, right, because 5 times 20 is 100%. It doesn't do that. It doesn't go down to 0 like that. It actually curves, and we're going to show you that today. Now, animals do go extinct, but it's pretty hard. Let's see this. Right, because an exponential function is asymptotic to the x-axis, right? It really slows down as it gets close to 0, but it doesn't ever reach 0. Now, what happens is, in the real world, we do get things that go to 0. All right, but that last little bit hangs on. all right, trying to survive, usually. And the math says why. It's nothing to do with the animals. It has to do with the math. So let's see that. A contaminated site, this is a nuclear accident. So a contaminated site loses 20% of its radioactivity per year. What percent of the radioactivity will still remain 20 years later? Right? So this is a problem when we have nuclear accidents. So we have F of t, right? So it's 1 because it's up, right? We don't have a y-intercept. And we're losing 20%. So if we're losing 20%, we're at 80%. By now, we should know that's 0.8. So we have to do 0.8 to the 20th. So we need our calculator. And so 0.8 to the 20th is 0.01159. So we're going to make that a percent, and that's around, make sure I did this right, 0.8 to the 20th. Yep, that's right. All right, so it's around 1%, right? So 20 years later, it'll decrease. If it is losing 20% of its radioactivity per year, it'll get down to 1% in 2 years. But will it get to 0? And the answer is no. Chernobyl is never going to get to 0. Never. All right, it will get closer and closer to 0. But there will always be some radioactivity. There will be at some point in the distant future, people will say the radioactivity is acceptable levels. But it will not get to 0 because nuclear waste always follows an exponential decay function. It will get closer and closer. Now, when people don't understand exponential functions, they think that it acts like this blue line. So if you lose 20%, and 20% times 5 is 100%, all the radioactivity should be gone in 5 years. That's not what happens, right? Notice these are very similar, just like the interest at the beginning. And then the exponential function curves away from the linear line. Right, so let's write an exponential decay function. So it's f of t. There's our y-intercept where t equals 0. So it's 100 in this. And now we need to know the constant ratio. It's 90 over 100, which is the same as 81 over 90, which is the same. These last ones have rounding in it, so if you get out a calculator, they probably won't come out exactly as the same as the first two. But these both make 9/10, right? You simplify both of those, they're 9/10. And so we're going to use decimals for this. It's 0.9, right? So that's going down 10%, right? We're ending up at 90%. That's what 9/10 or 90/100 is. See. Do this one. Right, all of those make a half. Right, and it's because we should be using decimals there. You could write it with 1/2, but let's be consistent and use 0.5, right? We all know that 1/2 is 5/10. It's 0.5. Right, and if we want to check the other ones, yeah, they all simplify to 6/10. So 0.6 to the t. All right, so one of these is linear, one is exponential. We're going to write a function for each, label them. These last two have rounding in them, so it's not going to be exact. But all of these simplify to 0.8, and so this is exponential. It's decreasing by a constant rate. All right, so let's write our functions. Since we're doing exponential functions, that's probably the easier one. We started at 1,000, and we're going down 20%, right? We're going down 20% to get this 0.8 to the t. Write the linear one. Y-intercept plus 1,000. Okay, and it's f of t equals, now we're not using x, we're using t. So what is the slope? Right? The slope is negative, right? This has a negative 200 slope, right? Because we're going down 200 for every time period. Practice. So if half are eliminated, half are left. And we're going to do 3 rounds. Hopefully it goes into 128 nicely. Oh, it does. And so there will be 16 clears. Half of them and get down to 64, then get rid of half of those and get down to 32, get rid of half of those and get down to 16. So if we're losing 6%, right, we're at 94%. So we're going to write 0.94, and we want to know for 10 weeks, right? That's of t, this is f of 10. So it'll be 0.94 to the 10th. Again, you really want a calculator. Now, again, if you don't have a good calculator, you can keep hitting on your calculator, usually 0.94 times 0.94 times 0.94 and so on. And I'm getting approximately 53.86 and a bunch of other numbers, which is around 54% of their customers. If you're losing 6% a week, 10 weeks later, you'll have only 54, a little more than half of your customers will go there. Now notice, it's not as bad as 60%. That's because instead of going straight down, it starts fast, but then it curves, right? It curves. So we have a $100,000 car. And, right, so if we're down 15%, where are we at? We're at 85%. And we're doing 7 years. Let's see. This is actually it's usually worse than this, I believe, in the real world. So this is 100,000, and we're times 0.3205, and some other numbers. And so your $100,000 car, 7 years later, and different cars lose different percentages every year. And it's based on the perceived value in the marketplace, right? If you have a car that doesn't break down a lot, that percent is going to be low. 50% is on the low side. But if you have a car that breaks down a lot, right, it breaks down a little, you get a low percent. Did I say that right? If it breaks down a lot, you're going to lose a higher percentage each year. Oh, that was for dollars. 200 over 500 equals 2/5, which is 4/10, which is 0.4. And if you're interested, you could double check the other ones. They should all make 0.4. Right, so which one is linear? Which one is exponential? is the exponential. This one is the linear. The exponential is f of t, starts at 400, 0.9 to the t. And linear, right, so f of t, the y-intercept, add 400, and the slope is negative 40. Negative 40 times t plus 400. We go down 40, right? We're going down 40 for every time period, another 40.